Tonight, we're going to follow what your first 1,000 days on the moon would actually be like. The first day would feel historic. 4 people stepping onto a world where only 12 humans have ever stood, beginning a stay that would last 2 years and 9 months. But after the landing, the moon would stop feeling like a destination and become the environment you had to survive every hour. Over those 1,000 days, you would experience only about 34 lunar sunrises. Each one would begin nearly 2 weeks of continuous daylight, followed by nearly 2 weeks of darkness. Outside the habitat, there would be no air, no weather, and no natural protection from radiation or extreme temperatures. Without a pressurized suit, consciousness would last only seconds. Inside, every ordinary part of life would depend on machinery. Every breath would be produced and recycled. Every drop of water would be recovered. Food, power, temperature, pressure, and waste would have to be managed continuously, while lunar dust worked its way into seals, joints, filters, and equipment. The greatest challenge would not be reaching day 1. It would be keeping the same fragile system alive through day 100, day 500, and eventually day 1000, when the nearest replacement part is still 3 days away. By the end of tonight, you'll understand how life would change across those first 1,000 days, what the moon would do to the body, the mind, and the machines keeping both alive, and why living there would mean maintaining a small piece of Earth that could never be allowed to fail. Before we get started, take a second to like and subscribe. It really helps the channel. Now, let's begin. Your first day on the moon begins before the landing legs ever touch the ground. The descent engine fires, pressing the crew back into their seats as the grey surface rises toward the window, faster than the eye expects. What first appeared flat and distant begins resolving into craters, boulders, and shadow lines sharper than anything seen on Earth, because there is no atmosphere to soften an edge. Outside, the engine makes no sound. The moon has no air to carry it. Inside the cabin, the crew feels only a metallic vibration traveling through the structure, a low mechanical hum beneath the voices and breathing in their helmets. At this distance from the ground, the spacecraft is no longer simply transporting people. It is a stack of instruments repeatedly confirming that altitude, speed, fuel, and position remain within limits. Every reading matters. There is nowhere to circle back toward, and no second landing attempt waiting if the first one fails. Exhaust strikes the surface and throws lunar dust outward in long, shallow arcs. On Earth, a landing rocket creates a choking cloud that rolls, expands, and hangs in the air. On the moon, there is no air to hold the particles together. The dust does not billow. It flies. Each grain follows its own clean trajectory, traveling hundreds of meters before falling back to the surface. Fast, silent, and nearly horizontal, like shrapnel thrown sideways from an explosion nobody heard. Then, the legs touch the surface. The engine cuts out, and for the first time, there is a silence with no comparison anywhere on Earth. Not library quiet, not a hushed hillside at dawn. This is the silence of a world with no medium at all to carry sound. No wind to hiss through anything. No traffic, no running water, no bird song. The only sounds left belong to the body and the machine, breathing, and the faint cycling of the air system pushing filtered air across a face. Listen closely enough, and it is possible to hear the blood moving in your own ears. For a moment, no one moves. There is nothing left to say that the silence has not already said. This is not the arrival anyone imagined. Not triumph, not wonder. Just absolute, uninterrupted silence. And the first proof that expectation means nothing on this world. It would not be the last shock of the day. The view outside is wrong before anyone can explain why. The brain expects a horizon that fades, blue sliding into white, distance softened by haze. None of that exists here. The ground is a flat, powdery grey stretching in every direction, and it ends too soon. The moon's radius is barely more than a quarter of Earth's, and that tighter curve pulls the horizon in close. Stand at eye level, and the edge of the world sits about 2.5 kilometers out, a distance a person could walk in half an hour. On Earth, that same horizon sits twice as far, a full hour's walk away. Past that line, everything simply drops out of sight, and the whole world feels smaller than it has any right to feel. Above it, nothing softens the sky either. No atmosphere means no scattered light. So the sky over the grey ground is the total black of open space. The stars do not twinkle. There is no air left to blur them. The sun burns unfiltered, fierce enough that looking near it would damage the retina in seconds. No blue, no haze, no horizon glow. This is the sky the crew has come to live under. That was the view. Now came the body. Standing up here means relearning something the body has never had to think about. The geometry of standing has not changed, but the muscle memory has not caught up to it yet. Surface gravity measures about 1.62 meters per second squared, 1/6 of the pull it has calibrated itself to since birth. In local terms, a person weighs roughly 13 to 15 kilograms, about the weight of 2 packed suitcases. But the muscles do not know that. They still fire at full Earth strength, and a body built for 6 times this pull produces wildly disproportionate force the instant it tries to stand. The first step is a stumble. The foot rises too fast and too high. The body pitches forward. The inner ear, tuned for a lifetime to one steady pull, sends signals that no longer match what is happening. Not effortless, not graceful. Every movement overshoots. Every correction overcorrects. Apollo astronauts described a persistent feeling of falling in slow motion, a disorientation that eased with practice but never fully disappeared. Harrison Schmitt, the geologist who walked on Apollo 17, compared it to a trampoline that never gives back the force expected. Push down, expecting resistance, and the ground answers wrong. The fall happens slowly enough to feel recoverable. It usually isn't, and here is the part that matters more than the stumbling. Apollo crews only endured this disorientation for 3 days at most, before heading home. This crew will spend weeks adapting, not days, and every extra week the body spends recalibrating to 1/6 of its expected gravity is a week of quiet change building in muscle, in bone, in the heart itself, change with consequences that belong to the months still ahead, not to this first hour. The mission has effectively begun collecting its own data on a question no short Apollo stay ever answered. And the first entry in that record is a stumble at the base of a ladder. None of that is the immediate problem. The immediate problem is smaller and far more urgent. Get inside, seal the hatch, pressurize the cabin, confirm system by system that everything meant to keep 4 people alive on a world built to kill them in minutes is actually verifiably working. Because outside that hatch, the moon has already made one thing clear before a single boot has properly learned to walk on it. It gives nothing away for free. Not the silence, not the ground underfoot, not even the horizon a person can see. Everything from here forward will have to be carried, built, or manufactured. The air behind that hatch is the first thing on the list, and it does not yet exist. Not for one day of the 1,000 still ahead. The hatch closes behind the crew with a hard mechanical seal, and the cabin begins pressurizing almost before anyone has had time to feel relieved. Getting inside was the goal, but inside is not automatically safe. It is safe only because of what fills the space, and that thing does not exist here on its own. The habitat itself is not generous. Design concepts for an early lunar surface outpost like this one call for somewhere between 40 and 50 cubic meters of usable interior, close to the floor space of a small studio apartment. For one person that would already feel tight. For 4 people eating, sleeping in shifts, and working in the same volume for 1,000 days straight, it is closer to a container than a home. The walls of that container are not simple partitions. Layer after layer of thermal insulation wraps the structure to hold heat in against a universe that wants to pull it away. And beneath that sits shielding, meant to absorb the impact of micrometeorites, too small to track from Earth, but fast enough to punch through bare metal. Every layer earns its place. None of it is decoration. Inside that container, the atmosphere reads familiar. Roughly 79% nitrogen, 21% oxygen, held near one standard atmosphere. The same mix and pressure as sea level on Earth. Breathe in, and the body recognizes it instantly. Nothing about it feels foreign. That familiarity is the trick. Every molecule of it was either carried up from Earth inside compressed tanks, or built on site. Water pulled apart by electrolysis into hydrogen and oxygen, the oxygen kept, and the hydrogen stored or vented. None of that air originated outside these walls. None of it ever will. The moon does not manufacture breathable air, and no process on its surface is ever going to change that. Step past the outer wall, and the fact becomes total. What passes for an atmosphere out there is an exosphere, a plain word for almost nothing, a scattering of stray atoms so thin that individual particles travel long ballistic arcs and rarely collide with each other at all. For any human purpose, it amounts to a vacuum. No pressure, no oxygen, nothing to breathe. The sealed air behind the hatch is, without exaggeration, the only breathable environment within roughly 384,000 kilometers in any direction. It exists in that one volume because engineers put it there, and nowhere else in that entire distance, which is where the real danger sharpens. A pinhole in the wrong seam is not a maintenance note. It is a straight leak into hard vacuum. The atmospheric system can compensate for small seepage, topping off pressure, filtering, adjusting quietly in the background. But here's where it gets strange for anyone used to thinking of walls as safe. A strike from a micrometeorite, or a single seal giving out around an airlock port, can open faster than any system can answer. How much time does that actually leave someone? Not much, and less than it sounds. This has already played out once, elsewhere. On the International Space Station, a persistent air leak took investigators years to fully track down and fix, tracing it centimeter by centimeter through a module, testing patch after patch. That slow hunt was possible because the station had what this habitat does not: rotating crews, regular resupply flights, and a rescue vehicle docked and ready at all times, an actual way home on short notice. Out here, there is no ready vehicle, no neighboring module to retreat into and seal off, no capsule waiting on the far side of an airlock. A serious breach on this mission cannot be a slow, years-long investigation because nobody would survive long enough to finish it. It is an emergency measured in minutes, not a controlled evacuation, not a depressurization anyone could calmly walk away from. So the inspection never stops. Every seal, every joint, every viewport frame, every hatch connection gets checked, and then checked again, on a schedule that does not loosen with time or with familiarity. Not on day one, when the walls are still new and every sound in them still gets a second look. Not on day 500, when the routine has gone quiet through sheer repetition. Not on day 999, one day short of the mission's full length, when exhaustion makes skipping the smallest step feel harmless. There is no version of this schedule that gets to relax. A seal that held perfectly on day 400 can still fail on day 401. Familiarity with a system is not the same as safety from it, and out here the two are easy to confuse. The crew checks anyway, every time, because the alternative to checking is finding out the hard way, and there is no version of finding out the hard way that ends well. That is the actual shape of the bubble the crew is living inside. Not a home with air included. A pressure vessel, thin-walled, holding back a vacuum that would not hesitate. The moon has already made its terms clear about the ground and the silence and the horizon. Now it makes them clear about the one thing a body cannot go 5 minutes without. Nothing in here is owed. Nothing in here arrived on its own. It was carried or it was manufactured, and either way it has to be watched. Every day, for as long as the mission runs. Think about what that really means, laid out plainly. A planet gives its residents air without asking anything in return. It just happens. Atmosphere held in place by gravity and geology laid down over billions of years. Breathed in without a single thought, spent on where it came from. Here, the crew spent months of engineering, tons of launch mass, and a running electrical budget just to keep that one privilege intact inside a container the size of a small apartment. Step outside that boundary, and the privilege ends immediately, replaced by an exosphere that cannot sustain a human lung for even a single breath. The air was only the first entry on that list. The second one waits just past the hatch, and reaching it means opening the seal on purpose. Nobody steps outside a lunar habitat the way they step outside a house. There is no door, no porch, no quick look at the sky before deciding on a jacket. Getting outside starts well over an hour before anyone touches the outer hatch. Sealed into a suit that is not clothing at all, but a spacecraft built to fit one body. It holds its own pressurized atmosphere, its own thermal control, its own radiation monitoring, its own carbon dioxide scrubbing, its own communications link back to the habitat. It is, in every meaningful sense, a second, smaller vessel, worn rather than flown. That vessel does not come free. Gloves alone cut hand dexterity by roughly half, turning a task as small as flipping a switch into deliberate, effortful work. The helmet narrows peripheral vision to a fraction of what the eye is used to. Every joint at the shoulder, the elbow, the knee, fights against the pressure differential, holding the suit rigid against vacuum. So bending an arm costs real muscular effort instead of a passing thought. Here is the part that catches people off guard. On a world where the body weighs only a sixth of what it did at home, the suit is what makes a movement clumsy, not the gravity. Precision gets harder exactly where the work demands more of it. And the suit runs on a clock nobody can argue with. Oxygen, battery charge, and the suit's capacity to scrub carbon dioxide out of the air all run down at fixed rates. And together they set a hard limit on how long an excursion can last. When that limit arrives, the work stops and the crew returns, finished or not. There is no arguing with a battery reading 0, no negotiating with an oxygen gauge, no version of the schedule where the suit waits for the job to be done first. Only once all of that is sealed, checked, and running does the outer hatch finally open onto the surface itself. And underfoot is where the real hazard of this section begins. The boots press into a layer of fine grey powder, and that powder is not soil, not sand, not dirt in any sense the word normally carries. Earth's version of ground dust spent millions of years being rounded and softened, tumbled by water, scoured by wind, broken down by living things decaying into the ground beneath them. The moon has none of that. Every grain underfoot is the product of billions of years of micrometeorites, hammering volcanic rock into fragments, with nothing afterward to smooth a single edge. Look at one of those fragments closely enough, and it resembles a shard of broken glass. Jagged, hooked, fractured in sharp, interlocking planes that catch on fabric, metal, and skin instead of sliding across them. And they carry a charge. Constant bombardment from unfiltered ultraviolet light, and the solar wind strips electrons straight off the surface of every grain, leaving it clinging with a static pull that fabric cannot shed, and brushing usually makes worse. driving the particles deeper instead of off. A sandstorm on Earth still wears its edges down a little more with every gust, grain grinding against grain until the sharpness fades. Nothing here ever performs that softening work. Every particle that lands on a boot or a glove today is exactly as sharp as it was the moment a micrometeorite forged it, and it will still be that sharp on day 1000. Apollo found this out inside days, not years. Every crew that walked on the surface came back with dust packed into glove joints, worked into helmet ring connectors, and carried through the airlock into the cabin air, where it went airborne in the warmth and got breathed in. Harrison Schmitt, the geologist on Apollo 17, described what he called lunar hay fever: sneezing, watery, reddened eyes, a raw throat that took days to settle. The dust itself smelled like spent gunpowder, freshly broken regolith reacting the moment it touched moist cabin air. A flight surgeon who later handled the returned samples noted something stranger still. The allergic response seemed to worsen with each new exposure, as if the body were building a growing sensitivity rather than getting used to it. Apollo's longest stay was 3 days. This mission counts its days in the hundreds. Not slightly worse, categorically different. A 2025 study out of the University of Technology, Sydney, offered a cautiously reassuring note. Testing next-generation lunar dust simulants against ordinary urban air pollution and finding the simulants did less damage to human lung cells in the lab. But the same researchers were careful to flag what their simulant could not capture: the electrostatic charge and the raw, freshly fractured surface chemistry of the real thing. Nobody has ever breathed actual lunar dust for months or years running. What that does to living tissue over time remains honestly unknown. So the dust does not stay outside. Every excursion drags a little more of it back through the airlock, and across 1,000 days that becomes a chronic condition rather than a passing irritation. It degrades air filters. It scratches optical surfaces. It works into the seals that keep the habitat pressurized. The same seals inspected on a schedule that never relaxes. Concepts for managing it exist: electrostatic cleaning systems, air curtains at the airlock, suit designs meant to leave the contaminated exterior permanently outside the pressurized volume. None of them have been proven on the actual surface, under actual conditions, over actual years. Apollo crews carried this problem home with them and let doctors study it for a few days before it faded. Here, nobody gets to set the problem down. Every trip outside adds a little more to what the filters, the seals, and eventually the lungs have to absorb, and none of that total ever moves backward. The suit gets the crew out there. The dust makes sure the outside never entirely leaves with them. Dust announces itself. It cakes a glove, clouds a visor, works grit into a seam where a hand can still find it and try to wipe it away. The next hazard waiting on the other side of that seal announces nothing at all. Earth carries an invisible magnetic bubble around itself, generated deep in a churning molten core. And that field, the magnetosphere, deflects the vast majority of energetic charged particles arriving from the sun and from deeper space. It is the reason a body on Earth's surface can go a lifetime without noticing any of this. The moon never built one. Its core cooled and locked still ages ago, far too small and far too quiet to generate a comparable field of its own. And whatever faint magnetism lingers in patches of the crust does nothing to shield a habitat standing exposed on the surface. So 2 separate kinds of radiation reach this ground completely unblocked, and neither one ever takes a day off. The first is constant, a steady rain that never lets up. Galactic cosmic rays are high-energy particles flung outward by supernova explosions and other violent events scattered across the galaxy, arriving from every direction, all the time, indifferent to whether anyone is standing beneath them. They are also brutally hard to stop. Their energy is high enough to punch through meters of solid material, and when they finally strike something dense enough to slow them, they often shatter into showers of secondary particles that keep traveling anyway, scattering the original problem into several smaller ones. More shielding does not simply mean less exposure. Sometimes it means a different kind of exposure, and engineers designing a habitat wall have to account for both. In 2019, China's Chang'e 4 lander, sitting on the moon's far side, put an actual number on that rain. Roughly 13 micrograys reach the surface every hour, day or night, sunlit or shadowed, a rate 2 to 3 times higher than what astronauts absorb aboard the International Space Station, where the same terrestrial magnetic field still offers a measure of cover even hundreds of kilometers up. A crew member aboard the station gets a partial umbrella. A crew member standing on the lunar surface gets none. 13 micrograys sounds like nothing. A single dental X-ray delivers a dose in roughly that range. Here, that same small dose arrives every hour, every one of the 1,000 days on the schedule, whether the crew is outside working or sealed indoors asleep. There is no version of the day where the counting stops. Add it up across 1 year, and the running total climbs into a real fraction of NASA's career radiation limit for an astronaut, the ceiling meant to hold a career's worth of risk to an acceptable level. Add it up across the full 1,000 days, and depending on how much shielding the habitat actually provides, and how many hours the crew spends outside it, that total edges toward the limit or past it. Nobody can say exactly which, yet. No one has carried a body through this particular dose for this particular length of time before. The crew is, in a very real sense, the study. And the background rain is not even the sharper danger. The sharper danger arrives with no warning pattern at all. Solar particle events are bursts of high-energy protons the sun throws off during major flares and eruptions called coronal mass ejections, clouds of charged material blasted outward from the sun's outer atmosphere, and there is no reliable way to know one is coming until it has already left the sun and is already on its way. A minor burst might raise surface radiation for a few hours and fade. A major one belongs to an entirely different category of event. One measured not in a background hum, but in a single dose large enough to matter on its own. Wait, one of that scale actually happened. In August of 1972, in the 16-month gap between the Apollo 16 and Apollo 17 missions, when the surface happened to be empty. Had a crew been standing outside during that storm, the dose would very likely have been lethal within hours. No shelter could have saved them, because in 1972, nothing on the surface was built to shelter anyone from it. Apollo 16 had already come home. Apollo 17 had not yet launched. The gap between them was the only reason anyone walked away from that particular 16 months unhurt. It will not always miss. Across a 1,000-day stay, the odds of running into at least one solar particle event of real severity are not remote. Not a freak possibility to plan around, and hope avoids you. A statistical certainty, somewhere on the calendar, waiting on a date nobody can predict, arriving whether the crew is ready for it, or halfway through an EVA on the far side of the habitat, which is why the habitat holds a dedicated radiation shelter inside it, a heavily reinforced enclosure built into or beneath the main structure. Walls thick enough to blunt a proton storm, the ordinary hull cannot. And why the warning window, once a major event is detected, can be as short as 15 minutes. 15 minutes to notice the alert, drop whatever the day's task was, seal any open hatch, and get every person behind that shielding before the surface dose spikes towards something the body cannot absorb safely. Dust settles visibly into a glove and stays there, something a hand can find and remove. This leaves no mark on skin, no smell, no weight anyone can feel, no proof at all that anything happened. It only adds quietly and without pause, to a running total that never moves back down, hour after hour, cycle after cycle, for as long as the mission runs. The number the crew carries home, if they carry it home at all, will be one nobody can fully explain until long after the fact. Radiation is not the only thing outside the walls working steadily against the machine. So is the temperature. Air was the first item on that list. Dust was the second. Radiation was the third. Temperature is the fourth, and unlike the others, it never even pretends to hold steady. The lunar surface is one of the most thermally extreme environments in the inner solar system. For roughly 14 Earth days at a stretch, the sun sits overhead without setting, and the ground climbs to about 127 degrees Celsius, hotter than the inside of a kitchen oven running its self-cleaning cycle. Then, for another 14 Earth days, the sun drops below the horizon and does not return, and the surface plunges to around minus 173 degrees Celsius, colder than the air inside a cryogenic freezer used to preserve lab samples, cold enough that oxygen itself would turn to liquid and pool on the ground. Day to night, the swing between those two extremes runs close to 300 degrees, a gap wider than the distance between the floor of a pizza oven and the inside of a walk-in freezer, crossed twice a month, forever. Nothing softens that fall. There is no atmosphere to slow the transition, no wind to carry warmth from the sunlit side, no ocean to hold heat in reserve, no cloud layer to trap the last of the escaping warmth overhead. The moment the sun sinks, the ground simply radiates everything it has stored straight out into space, with nothing in the way to catch it. Within hours, the surface temperature falls by hundreds of degrees. It would be reasonable to expect some warmth to rise up from below and slow the loss. It does not. The regolith underfoot is a nearly perfect insulator, its structure so porous in a vacuum that heat barely moves through it at all, more like a sealed vacuum flask than a blanket. Whatever warmth sits in the deeper layers stays trapped there, doing nothing to soften the surface above. Not a buffer, a wall. The South Pole is often described as the gentler option, and Artemis-era planning targets it for exactly that reason. There, the sun stays low near the horizon rather than climbing and setting the way it does at the equator, producing stretches of near constant light in some spots and permanently shadowed craters nearby that never warm at all. The picture did not hold. Even that milder setting is not mild, not forgiving, not close to anything human infrastructure has been asked to survive continuously for years, and the polar sites are no exception to that standard. The habitat has to sit through all of it, every single cycle, every exterior surface, every seal, every exposed mechanism is built to take a swing of hundreds of degrees, and that swing does not happen once. It repeats on a period close to 29.5 Earth days, day into day again, roughly the length of a full calendar month spent baking, and then freezing without pause. Stretched across 1,000 days, that works out to roughly 34 complete cycles of extreme heating and extreme cooling, one after another, with no season of relief in between. Materials do not shrug that off. They expand under heat and contract under cold, and every repetition of that motion works against whatever is holding the habitat together. Think of a paperclip bent back and forth. The first few bends do nothing visible. Nothing changes. Then, somewhere past a threshold no one can see coming, the metal weakens and snaps. Joints loosen the same way. Fasteners back off by fractions of a millimeter. Adhesive bonds and gasket seals grow slightly less pliable with every pass through the extremes. The same seals the crew inspects on a schedule that never relaxes. Cycle after cycle, never recovering the flexibility lost the time before. 34 cycles is not a large number to say out loud. It is a large number to survive intact. Airlock seals, viewport frames, panel joints, the fasteners holding external plating to the frame underneath. All of them ride the same swing, all of them lose a fraction of their integrity every single time, and none of that loss reverses no matter how many cycles pass afterward without incident. The International Space Station goes through its own version of this, cycling through day and night, roughly every 90 minutes as it circles the planet. But its swing is smaller, and a sliver of Earth's own atmosphere still reaches up to ease the transition even at that altitude. This habitat gets no such easing. The swings here are slower, but far more extreme, and they run inside a hard vacuum with nothing standing between the machine and the full force of the difference. Cycle by cycle, the effect is not damage anyone would notice in a day or a week, or even a month. It is a clock, running in one direction only, counting down joints and seals and bonds that will not be replaced from any store nearby, and it does not pause to let anything recover. Exactly how much strength is left in any given seal by the far side of the mission is not something anyone can measure from 1,000 days away. That question stays open, and it stays open on purpose. Nobody has run a habitat through 34 of these cycles before. That clock was already running before the crew had felt the cold directly even once, running through the walls, the seals, the frame itself, all day and all night, whether anyone on board was watching or not. The first full night on the surface was still ahead of them. It was coming, and there would be no daylight to soften its arrival. Then, the sun dropped below the horizon and did not rise again for 2 weeks. Air, dust, radiation, and temperature were the first 4 entries on the list the moon kept against the crew. Power was the 5th, and it did not introduce itself gently. For 14 Earth days, the exterior temperature settled toward minus 170 degrees, and the solar panels that had carried the habitat through daylight, quietly, almost invisibly, went completely dark. From that moment, every watt the crew would use for the next 2 weeks had to come from what was already stored. Batteries and regenerative fuel cells charged during the sunlit stretch are now asked to carry everything at once. Heating, atmospheric processing, interior lighting, communications with Earth, water recycling, waste management. The computer's monitoring all of it, watching the reserve tick downward the way a fuel gauge does on a long drive with no gas station for 200 miles. None of that runs on hope. If the stored reserve ever proves insufficient, the failure does not arrive all at once. It arrives in a sequence, and the sequence is knowable in advance, which makes it no less frightening to watch play out. Heating falters first, equipment freezes and cracks, the atmospheric processes slow next, and carbon dioxide climbs while oxygen quietly falls, the numbers drifting the wrong direction on a display nobody in the habitat can afford to stop checking. The margin between an ordinary night and an emergency is thin. It is real. It does not forgive a miscalculation in either direction, and there is no help arriving from outside to widen it. This was not a one-time trial to get through and forget. The same 14 days of dark would repeat roughly 34 times across the full mission, once every lunar month, for as long as the crew remained without a better source of power. Get through the reserve calculation correctly this time, and the next one still has to be gotten through correctly too, and the one after that on a surface that offers no partial credit for a night, mostly survived. There is a fix for this, on paper. NASA and the US Department of Energy have spent recent years developing what is called a fission surface power system, a small nuclear reactor purpose-built to deliver electricity whether the sun is up or not. Somewhere between 40 and 100 kilowatts, running continuously. Narrated slowly, that is enough power to keep something like 40 to 100 ordinary houses lit, heated, and running without pause, day after day, with no sunset ever able to interrupt it. Through 2025 and into 2026, development contracts were extended to Lockheed Martin, Westinghouse, and other partners. working toward a demonstration reactor on the lunar surface with a target date of 2030. A working reactor would end this particular fear outright. It does not care whether the sun is up. It does not run down after 14 days and wait to be refilled by daylight. It simply keeps producing night after night on a schedule that has nothing to do with the moons. But here's the problem. No reactor like that has ever operated on the moon. Not one. Not for an hour. The hardware does not yet exist in a form that could fly. And a mission that begins before fission arrives has nothing to fall back on but sunlight and storage. That turns every 14-day night into an endurance test. And an endurance test has a very specific failure mode. One battery cell does not stay one failed cell. It cascades. So the crew sits inside and waits it out. Outside, the ground has gone invisible. There is no reflected moonlight to soften the dark, because there is no other moon here to reflect it from. Only starlight too faint to cast a shadow, and Earth itself, hanging in the black sky close to 4 times the size the full moon ever appears from a backyard on Earth on a clear night. A blue and white disk, bright enough to trace the outline of ground and crater rim, far too dim to work by. That is the entire natural light budget for 2 straight weeks. Everything else, every lit surface inside the walls, comes from a bulb, a panel, a screen, 14 days under artificial light, sealed inside a pressurized container. No door to open except for a genuine emergency. The walls that felt generous during the active first days start to feel closer than they measure. The monitoring checks that carried real urgency under sunlight settle into something quieter and more repetitive, timed now to the low hum of machinery instead of the rhythm of a day that no longer exists outside. And the sense of standing on another world, the feeling that made the landing enormous, begins, almost without anyone noticing the exact moment, to thin out. What replaces it is not despair. It is something plainer and more lasting. Not an adventure that happens to include some risk. Not a milestone worth marking on a calendar. A hostile environment that happens, for now, to be survivable. And nothing more generous than that. The crew had trained for danger, briefed on it, drilled on it, expected it in some recognizable form. What they had not quite braced for was how ordinary that danger would start to feel. Running quietly in the background of every one of these 14 nights, needing nothing dramatic to kill anyone. Only a battery that gives out an hour too soon. The night would end. The sun would return. The panels would wake. The reserve would climb back up. And the count of remaining nights like this one would drop by a single digit, from roughly 34 towards 0, with no way to skip ahead. The recognition would not climb back with the reserve. It would still be there in the light, waiting for the next sunset to prove it right again. That first dark night had answered a question nobody in the crew had gotten around to asking out loud. If the moon was this hostile, what exactly did it give back in return? The answer, looked at directly, was nothing. Not air, not water sitting free on a surface, not soil a plant could grow in without processing it first, not fuel, not shelter, not so much as a beam of usable building material lying on the ground waiting to be picked up. Every gram the crew breathed, drank, ate, or built, with either rode a rocket from Earth or came out of the regolith through machinery that is still mostly unproven, still mostly bench prototypes and small-scale trials rather than working hardware standing on this surface. And riding a rocket from Earth was never cheap. A kilogram of anything landed on this surface cost tens of thousands of dollars, more than the price of a small car, spent to deliver a single sack of flour. There was one exception on the books, or at least the appearance of one. Water ice, almost certainly locked inside craters near the South Pole that never once see sunlight. Multiple orbiting spacecraft had picked up hydrogen signatures consistent with buried ice for years. And in 2024, a NASA study confirmed those signatures stretched across south polar craters beyond 77 degrees latitude. Widespread, consistent, hard to explain any other way. But the reality was different. Nobody has drilled into one of those shadowed craters. Nobody has confirmed how deep the ice sits, how concentrated it is, or whether a machine could actually reach it and turn it into water anyone could drink or oxygen anyone could breathe. Not a water tank, not proven, not touched. A signal from orbit, and nothing more than that. The distance between a promising reading in the data and a working extraction plant on the surface is measured in years of engineering nobody has done yet. For this crew on this mission, that promise changes nothing. They live on what they brought. Set that against the length of the stay. On Earth, that span is long enough to earn a graduate degree, watch a child grow from a newborn to its first spoken words, or sail across an ocean and back. On the moon, 1,000 days means something else. Roughly 34 sunrises, 34 sunsets, and 34 stretches of total darkness, and every one of those cycles repeats the same list of demands in the same order, with no cycle excused for having gone well the time before. Power has to be managed, heat has to be moved, air has to be scrubbed, water has to be reclaimed, dust has to be kept out, radiation has to be tracked, every seal, every joint, every filter has to be checked, again, correctly, every time, for the whole stretch. On Earth, a tripped breaker or a clogged filter is an afternoon's annoyance. Out here, that same small failure can turn the outside air into something that kills an unsuited person in under 2 minutes, and can compromise a depowered habitat within weeks. That is the shape the first days had already revealed to anyone paying attention. The moon is not a destination that rewards you for reaching it. It is a continuous problem that starts the moment the engines cut out and does not let up. And the first real shock was never that the place was dangerous. Training had covered that already, thoroughly, for years. The shock was that the danger carried no drama with it at all. No storm to shelter from. No earthquake to ride out. No predator circling the habitat at night. Not dramatic danger. Ambient danger. Woven into everything at once, into every charged grain of dust, every unshielded particle of radiation, every degree of a swing wide enough to bake and then freeze the same patch of ground twice a month, and into the simple, total absence of anything a human body actually needs to stay alive. 1 week in, every system still read nominal. Nothing had failed. The mission clock showed 993 days remaining, which was another way of saying 141 more weeks of exactly this. The filters replaced this morning would need replacing again. The seals checked today would degrade a little further tomorrow, and the day after that. The food eaten this week came from a supply that would never restock itself. What comes next was never going to be one dramatic failure the crew could point to and call the moment. It was going to be the plainer work of keeping every system running, every day, for 141 more weeks, inside a sealed box sitting on a surface that never stops trying to wear that box down. That is the moment the moon stops being a place anyone travels to. It becomes a machine you survive inside instead, one that demands constant attention precisely because the environment outside its walls is constantly working against it. The moon does not know or care that anyone arrived. It offers no welcome, and it never will. It is simply continuing to be what it has already been for something past 4 billion years. A span so long that if it were compressed into a single calendar year, the whole of human history would fit inside the final seconds before midnight. A dead, irradiated, dust-covered rock with no air, no water, no warmth, and no mercy built into its design. What happens across the 993 days still ahead depends on exactly one thing: whether the machinery this crew brought with them can keep outlasting the world they brought it into. If the moon is a machine you survive inside, then a day on the moon is a day spent tending it. Waking does not begin with a window or a smell of coffee drifting from another room. It begins with numbers, atmospheric pressure on a panel beside the sleeping compartment, oxygen level, carbon dioxide level, humidity, interior temperature, power draw against power generation, water reserve volume, filter differential pressure, not poetry, not a message from home. Every crew member reads these figures every morning because they are the only honest report on whether the night held. A value drifting outside its margin collapses the whole day into troubleshooting before breakfast is even opened. All values nominal, and only then does the day become the ordinary one, the maintenance roster, the one that repeats. That repetition is the real content of the mission. Not exploration, not discovery, not standing at a viewport working through the wonder of where you are. The habitat is not a building being lived in, it is a machine being kept alive, pressurized, thermally balanced, its air scrubbed and its water pulled back out of the air and off every surface, performing alone the work an entire planet performs for free. On Earth, photosynthesis across billions of tons of plant matter keeps the air breathable without anyone tending a valve. Oceans absorb and release heat on a scale no engineer has to manage. A magnetic field turns away charged particles with no crew oversight at all. Here, every one of those functions has been replaced by hardware someone designed, built, launched, landed, and bolted into place. And every part of that hardware is wearing down a little more with each day it runs. The day itself follows a shape fixed months before the crew ever left Earth. The clock inside the habitat holds to 24 hours by agreement, not by anything the moon provides. The first half hour goes to checks and hygiene, a sponge bath from a measured ration of recycled water, a vacuum toilet that pulls waste apart into liquid and solid, because nothing else works in 1/6 gravity. Breakfast is a pre-packaged meal brought back to life with heated water, eaten shoulder to shoulder in a galley barely wide enough to seat all four at once. The taste is adequate. The variety ran out weeks ago. By the second hour, the crew splits. 2 take up the maintenance roster, filters inspected, sensors calibrated, water lines checked, seals examined, yesterday's unfinished repairs picked back up. A third moves into a mandatory block of exercise, an hour and a half to 2 hours on resistance machines, and a cycling rig built for partial gravity, prescribed the way a medication is prescribed, not offered as a wellness option, because bone and muscle do not hold their strength here without being forced to. The fourth prepares for whatever the day requires outside the walls, an excursion, a science task, a repair that can only happen in a suit. Contact with Earth arrives in scheduled windows. A signal takes a little over a second to cross the distance one way, close enough that conversation almost feels normal, structured enough that it never quite is. The crew sends status, telemetry, medical readings. Mission control sends back priorities, engineering notes, and a short video link with family. That link is a lifeline and a reminder in the same breath. The faces on the screen are home. The walls around the crew are not. A second meal marks midday, a short overlap where all 4 confirm the afternoon's assignments, and the afternoon repeats the morning's shape, more maintenance, more exercise rotation, whatever science or construction the remaining power and hours allow. By the 16th hour, the formal schedule ends. What is left is about 2 hours before sleep, a final meal, a log entry, whatever the volume allows, a book on a tablet, music carried from home, Earth itself framed in a viewport no larger than a dinner plate. 2 hours does not undo 14 hours of operational demand. Sleep is scheduled for 8 hours. It rarely arrives as 8. And running beneath every hour of that schedule, mostly unnoticed, is the loop that keeps temperature itself survivable. Through the 2 weeks of lunar daylight, the habitat has to shed heat it never asked for. Exterior surfaces climbing past 100 degrees C under direct sun, while the crew's own bodies and the electronics running their lives add still more warmth, with no air outside to carry any of it away. Radiator panels bleed that heat into space as infrared, but how well they do it depends on their surface condition, their angle to the sun, dust settling onto them, and dulling their ability to radiate at all. Thermal cycling slowly warps the brackets holding them in place. The coolant moving through the system has to be watched constantly. Its flow, its temperature, its chemistry, because even a slow drift in any of those numbers tips the whole balance. Then the sun sets, and the entire problem turns itself inside out. The same radiators that spent 2 weeks throwing heat into space now bleed the habitat's own warmth into a sky sitting a few degrees above absolute zero, and heaters take over, drawing on the same reserves that keep everything else running through the dark. Twice a month, the system has to switch its whole operating mode, cooling to heating, in a turnaround measured in hours, valves and pumps and plumbing all forced through a transition under direct crew watch. A coolant leak on one of those nights, with heat critical and power thin, would not stay a small problem. It would become the one failure that drags every other vulnerability of the dark down with it. There is no window to crack open here, no outside air to let in and adjust the temperature by hand. There is only the loop, endlessly moving heat from where it is unwanted to where it is needed, required to keep working through every one of those cycles, for every one of the 1,000 days. The heaters, the pumps, the sensors, the loop that moves the heat from where it is unwanted to where it is needed. None of it means anything without the one thing sitting underneath all of it: electricity. Stop the current, and everything above it stops with it. The atmospheric processors go still, the water recycler goes still, the heaters go cold, communications cease, the lights fail, even the sensors built to warn the crew that something has gone wrong go dark along with everything else, so the warning never arrives. Electricity is not a convenience layered on top of survival here. It is the difference between a functioning refuge and a sealed metal container, freezing and suffocating at the same time. Every hazard already covered on this mission, the dust, the radiation, the swing between baking and freezing, is a hazard the habitat answers with hardware. And every piece of that hardware answers to the same current. Power is not one more item on the list of things keeping this crew alive. It is the layer underneath the whole list, the one nothing else on it can function without. For roughly 14 Earth days at a stretch, the sun sits high enough to make that current cheap. Solar panels convert somewhere between 20 and 25% of the light that reaches them, and the light reaching them is fierce, about 1,160 watts on every square meter of panel, with no cloud and no atmosphere to soften it. That is more raw power landing on a single square meter than a home oven pulls to run its self-cleaning cycle, arriving free all day, every day of the lunar daytime. On paper, solar looks like the easy answer. In practice, the moon works against its own gift. Dust settles across every horizontal surface, and lunar dust does not simply sit there. It clings, charged. The same electrostatic grip that got into gloves and helmet seals back at the very first airlock. A thin film across an array can cut its output by 10 to 15% within a single lunar day. Wiping it off risks scratching the coatings the panels need to work at all. Systems that repel the dust electrostatically instead of touching it have been proposed. None has been proven on the surface. Month after month, the contamination and the cleaning both wear the panels down together, and the system that looked robust on day one grows quietly less reliable with every one that follows. Thermal cycling adds its own toll, the same expansion and contraction that fatigues Seals elsewhere in the habitat now loosening solder joints, embrittling insulation, working mounting hardware slowly free. But daytime generation was never the real danger. The real danger is the dark. For 14 days, every watt the habitat burns has to come from what was stored before the sun went down. A conservative estimate puts continuous demand at around 6 kilowatts, enough to run 6 household ovens at once, without a single pause, for 2 straight weeks. Multiply that draw across a full lunar night, and the number lands close to 2,000 kilowatt hours of stored energy, something close to 2 months of an ordinary household's electricity use, compressed into 14 days of darkness. Storing that much energy is not free. Current lithium-ion cells hold about 250 watt-hours per kilogram, so 2,000 kilowatt-hours of battery works out to roughly 8,000 kilograms, close to the combined weight of 5 family cars, launched from Earth, landed intact, and bolted into a corner of the habitat for the sole purpose of keeping the lights on through one night. Delivering that mass to the surface runs anywhere from the tens of thousands to well over $100,000 per kilogram. That is the price of darkness, paid in advance, every single month. And the batteries do not hold steady. Every charge and discharge shaves a little capacity away. After a dozen full cycles, about 1 Earth year of operations, the loss becomes measurable. Past 30 cycles, somewhere near the 1,000-day mark, the bank may have given up 10 to 20% of what it once held. The margin that once looked comfortable thins with every night that passes, until one unplanned load, one system running a little longer than planned, could drain what is left before sunrise returns. There is another option on paper. Regenerative fuel cells use daylight power to split water into hydrogen and oxygen, store the gases, then recombine them at night to make electricity and hand the water back. Elegant. Lighter than a battery bank of the same capacity. And unproven, not at the scale a habitat needs, not in lunar conditions. The tanks still face the same thermal cycling that fatigues everything else outside. The membranes degrade. The stacks need upkeep no one has field tested for 1,000 days. And every gram of water that leaks out of that loop is a gram that cannot make power the following night. Which is why nuclear fission is not a luxury sitting somewhere on a future wish list. It is the technology this entire mission is quietly waiting on. A fission reactor splits uranium, turns the heat into electricity through Stirling engines or Brayton cycle turbines, and does not care whether the sun is up. No dust settling on a collector. No 14-day countdown to depletion. Day, night, storm, cold. It keeps running the same. It does not yet exist on the moon. A demonstration unit is targeted for 2030, and if the 1,000-day clock on this mission starts before that reactor lands, every single night still has to be bought the old way, out of a battery bank that is quietly, permanently losing capacity with each one it survives. Every other system on this mission can be inspected, repaired, and returned to full function. The power supply cannot. It can only be managed on its way down, watched, rationed, and coaxed through one more 14-day dark stretch, 30 more of them, then 30 more after that. What that slow decline means for everything drawing current from it, the water loop, the air loop, the food, is the next layer down. That next layer down is not one system, it's 4, running side by side, each one standing in for something a planet hands over for free. Water, food, breathable air, and what the body leaves behind after using both. Call the first of the 4 loops water, because after power it is the resource that matters most, and the one that sits closest to the body. A person needs 2 to 3 liters a day just to function normally. Multiply that by 4 crew members across 1,000 days, and the number climbs past 8,000 liters. closer to 12,000 once cooking, washing, and equipment cooling are folded in. Something close to 40 household bathtubs filled edge to edge. Shipping that much water from Earth was never realistic. It has to be caught and reused, over and over, inside the habitat itself. The hardware for that already exists. On the International Space Station, filtration beds, catalytic reactors, and a newer brine processor recover close to 98% of everything the crew loses: sweat condensed from cabin air, moisture from every exhale, processed urine. That is the equivalent of losing only 2 glasses out of every 100 poured. Astronauts already drink water that was, one cycle earlier, someone's urine. The system works, and it has been refined for more than 20 years. The lunar habitat inherits that hardware, but not the clean environment it was built for. Dust works into the recovery loop the same way it works into every seal on this mission, clogging filters, fouling catalytic beds, wearing through consumables faster than the orbital system ever had to answer for. 1/6 gravity changes how liquid separates from gas in every tank and pipe, in ways nobody has fully mapped. 98% is the number on paper. Even at 95, it still bleeds. Hundreds of liters, every 1,000 days. Water that has to come from somewhere. The obvious somewhere is the ice believed to sit inside permanently shadowed craters at the poles. Ground sunlight never reaches. Machinery that would run in cold close to liquid nitrogen's boiling point. 40 degrees colder than the lunar night this crew has already survived. Extracting it means mining and heating equipment operating in that cold, then transporting the product back for purification. And every one of those steps is still a concept, not a machine. Orbital instruments have already picked up the signature of hydrogen in that ground, but hydrogen in the data is not water in a tank. It could mean solid sheets of ice a shovel could cut. It could mean frost scattered thinly through ordinary regolith. It could mean isolated pockets buried under meters of bone-dry material a drill would have to fight through first. And which of those three is actually down there changes the entire extraction plan. No robotic mission has ever drilled into that shadow, confirmed ice at depth, and pulled out a usable amount. NASA's Viper rover was built to answer exactly that question. In 2024, it was cancelled before it ever launched. Not delayed, cancelled. The gap stays open. The recycling loop keeps working. It is not self-sufficient. It never quite closes. The second loop is food, and it fails somewhere no checklist measures. Morale. Resupply on a mission this long cannot deliver variety, so most of the menu is shelf-stable and pre-packaged, engineered for caloric density, nutritional completeness, and years of storage life while keeping mass and volume as low as possible. Built for calories and shelf life, not flavor. Crews on Antarctic winter rovers, submarines, and the 520-day Mars 500 simulation all report the same drift. A meal that tastes fine in week 1 becomes something to resent by month 3. Appetite drops. People start skipping meals they know they need. Weight falls at the exact moment the workload does not. A small hydroponic or aeroponic growth chamber, a tray of roots in circulating water and light instead of soil, can add a handful of fresh greens or herbs for relief. At the cost of volume, power, and crew time, this mission has little of to spare. It was never built to feed anyone. It was only ever built to remind them what fresh tastes like. The third loop is the air itself, moving invisibly until the day it does not. Each crew member burns through roughly the weight of a hardcover book in oxygen daily, and exhales a little more than a full liter bottle of water in carbon dioxide. Left unmanaged in a sealed volume with 4 people breathing, that exchange would make the cabin unbreathable within hours. Electrolysis splits water to replace the oxygen, hydrogen vented off, stored for fuel cells, or fed into a reactor that recombines it with captured carbon dioxide to produce methane and a little more water, closing part of the loop on itself. Sorbent beds and catalytic filters scrub the remaining carbon dioxide and the trace fumes that build up in a sealed volume, absorbing what they can, then releasing it again once heated, ready for another round. Every one of those parts has a service life measured in use, not years. Sorbent material loses its grip cycle after cycle. Electrode coatings wear thin. Every filter swapped in is one fewer left for later, and the whole inventory was sized before launch, from an estimate. If dust loads a filter faster than planned, or a malfunction forces a scrubber to work harder, that estimate is what buys the margin, and margins only shrink. The fourth loop nobody wants to discuss, and everybody depends on it. Waste. On the station, urine already feeds the recycling loop, and solid waste burns up with a departing cargo ship. Here there is no departing ship. Compaction and vacuum drying shrink the volume, but the mass has to stay somewhere inside a habitat where every cubic meter was already spoken for, and some of it, treated and packed into the walls, ends up doing one more job as radiation shielding. Failed filters, worn seals, spent components join it, a second inventory that only ever grows, 4 loops, and not one of them closes. Water leaks a little every cycle, food wears down morale a little every month, air runs on a countdown of spare parts, waste only accumulates. Each one is survivable on its own. What all 4 cost together in time, mass, and constant attention is the next thing this mission has to answer for. Time, mass, attention. Add those 3 costs together across 4 leaking loops, and one number rises above the rest. How much of every day belongs to the machine rather than to the reason the crew came here? Dust is where that number starts. It does not change character week to week. It only gets more persistent. Every excursion drags more of it through the airlock. Every mitigation slows the transfer, but never stops it. And it settles into ventilation ducts, sensor windows, and joints built for clean rooms. Not for a world with no weather to wash them clean. The cabin's air filters take the worst of it, cycling every breath through material rated for a certain amount of dust over a certain number of days. Apollo's evidence says real infiltration always beats the model. If the filters hold for 80% of their rated life instead of the full run, the crew burns through their spare supply 20% faster than the mission plan assumed. That is not a rounding error. That is weeks, then months, quietly pulled off the calendar. Seals wear down on the same curve. Every open and close of an airlock drives fine abrasive grains into the door gasket, and each cycle opens the channel a little wider. One cycle costs nothing measurable. 100 cycles, and the leak shows up on a gauge. A few hundred, and the seal has to come out entirely. The compartment depressurized, the old gasket peeled free, the seat cleaned, a new one fitted with a precision no glove was built to make easy. For an airlock used several times a day, 100 cycles arrive within weeks. A few hundred can arrive within the year. The spares for that job, like the filters, were loaded once before launch and never restocked. Radiation asks for nothing so dramatic. It is the quietest task on the daily list, and potentially the most consequential. It asks for a number, logged quietly every day from a dosimeter clipped to a flight suit, and a set of area monitors reading the habitat's interior. Shielding cuts the dose the crew absorbs inside the walls, but it does not erase it. Cosmic rays arrive at full strength and still push some of themselves through meters of material. Multiply a small daily increment by 1,000 days, and abstraction turns into arithmetic. A career limit sits at roughly 600 millisieverts, something close to the dose of 80 chest CT scans, spread across a working lifetime instead of a single afternoon. The habitat's walls alone let in something like a quarter to half of that entire allowance in 1 year. Add a single severe solar event on top of a dose already climbing, and the ceiling can arrive years ahead of schedule. When the monitors catch that kind of spike, the response is already rehearsed. The warning arrives fast, as little as 15 minutes, rarely more than a few hours, before the most energetic particles reach the ground. A shielded compartment behind water tanks, polyethylene brick, and bagged regolith takes the crew in, seals around them, and holds them there. Hours for a minor event, days for a major one. Every one of those hours is an hour the maintenance schedule does not get. The queue does not shrink while they wait. It is waiting for them when the door opens again. Widen the view and a pattern comes into focus that no single system reveals on its own. Power output droops under dust and thermal fatigue. Water recovery drifts a little further from full efficiency every month. Filters, seals, and sorbent beds all wear against a fixed inventory. Food variety narrows as the preferred items run out first. None of it announces itself in a single day. Each loss is a fraction of 1%, and the fractions never stop accumulating, because nothing about the environment doing the damage ever lets up. None of it is a single point of failure. All of it is a slow one. On Earth, a failing part gets replaced. Here, every spare was launched years in advance, against a prediction that may or may not hold. That prediction can miss in more than one way. Dust loading worse than any model assumed, a manufacturing flaw nobody caught before launch, a solar event that eats into maintenance time and lets a small problem grow unnoticed, while the crew waits out the shelter. However it happens, once the inventory is gone, there is no factory on the moon to make more. Consumption running ahead of plan leaves 3 choices only: cannibalize a lower priority system for parts, improvise a repair with materials never meant for the job, or shut something down and accept the loss of capability that follows. There is no fourth option. The regolith outside cannot yet be turned into a bolt, a gasket, or a circuit board, and it will not be able to for a long time. But here's what the maintenance log never quite says out loud. This is not a home the crew happens to live in while doing science. It is a prosthetic biosphere, a stand-in for an entire planet's worth of free functions, running on parts that wear out and hands that have to keep replacing them. Every task on that endless list, filters, seals, dosimeters, water tests, thermal checks, exists because the substitute needs tending. Always. Not chores, not interruptions, the life itself. Explorers second, caretakers first. The surface walks, the sample collection, the observations that filled the mission proposal, all of it gets fitted into whatever hour survives after the machine has been served. The science happens in the margins. The survival happens constantly, and it is never guaranteed. None of it forgives a missed step, either. The tasks stack in a sequence that has to run correctly, in order, and the coupling between them only tightens as the hardware ages. Skip a filter change and cabin dust climbs. Dust climbs and eyes and throats start to react. Irritation drags down sleep and focus, and a tired crew member is the one who misses the next task on the list. Skip a seal inspection instead, and a slow leak opens unnoticed, quietly drawing down an air reserve that then has to be made up from stores nobody budgeted for the shortfall. Nothing on this list fails alone anymore. Every missed task quietly raises the odds of the next one. 6 months in, the crew has cycled through roughly a dozen full swings from light to dark, about a third of everyone this mission will ever see. The tasks are familiar now. Familiarity does not make them lighter. It only strips away the novelty that once made them bearable. Everything still ahead is the same list. Run again and again. The same filters, the same seals, the same recycled water and pre-packaged meals, and grey surface, except the filters are older, the spares are fewer, And the bodies doing the work have spent half a year inside a gravity that has already begun asking its own price. The machine is aging. So is the crew keeping it alive. The habitat is not the only structure on the moon slowly coming apart. Everybody living inside it is doing the same thing, in its own quieter way. Nobody warns you about the spine first. Within weeks in 1/6 gravity, the discs between each vertebra begin to swell. On Earth, gravity presses down on those fluid-filled cushions all day and lets them ease back only at night. Here, the load drops to about 17% of what it is on Earth, not far from the same 1/6 fraction the whole body already carries, and the discs never fully compress again. The spine lengthens. ISS crews in near zero gravity have grown 3 to 5 centimeters taller during a single mission, about the width of a smartphone laid flat. 1/6 gravity would stretch the spine less than that, but not by much. And the swelling has nowhere polite to go. It presses on nerves and ligaments built for a mechanical load that no longer exists. Lower back pain, already the most common complaint on orbital stations, would likely settle in within months and stay. There is no physical therapist on the moon, no chiropractor, only a limited stock of anti-inflammatory pills and a set of resistance machines that may or may not be enough. That is only the opening symptom. Every bone holds its density because loading tells it to. Cells called osteoblasts building new tissue. Cells called osteoclasts clearing old tissue away. The two working in balance under the constant press of weight. Cut that press by 5/6 and the balance breaks. Osteoclasts keep working at close to full pace. Osteoblasts slow down, starved of the signal they need. The net direction is loss. In microgravity, astronauts lose bone density at roughly 1 to 1.5% a month in the hips, spine, and legs. Some of it comes back after landing. Some of it does not fully, not for years, and the deepest architecture of the hip bone may never fully rebuild. But here's where it gets strange. Nobody knows what 1/6 gravity does to that number, because nobody has ever stayed on the moon long enough to find out. The longest any human has spent on the lunar surface is about 75 hours. Barely 3 days, not enough time for bone remodeling to even begin. A NASA review published in 2021 looked at every scrap of available evidence and concluded that anything below roughly 0.4 times Earth's gravity is probably not enough to keep the skeleton and heart properly conditioned. Lunar gravity sits at about 0.16, well under that line. The only partial gravity evidence at all comes from mice. Between 2019 and 2020, researchers aboard the space station spun mice in a centrifuge to simulate lunar gravity for about 5 weeks. The results, published in 2024 in Scientific Reports, were not reassuring. Lunar gravity slowed the bone and muscle loss seen in full microgravity. It did not stop it. Extrapolating from a mouse to a person is an uncertain leap, but the direction holds. Stretched across 1,000 days, the cumulative loss could reach levels seen in elderly osteoporosis patients on Earth, a condition that normally takes decades to develop, compressed here into about 3 years. That is not an abstract number. A crew member who stumbles during a surface walk on day 20 risks a bruise. The same stumble on day 800, after months of quiet demineralization, risks a broken hip, wrist, or vertebra. Not a bruise, a mission-ending injury on a world with no ambulance and no hospital. Muscle follows the same slope. The legs, back, and core, the muscles that fight gravity hardest on Earth, suddenly have almost nothing to push against. In microgravity, calf muscle volume can fall by up to 20% within the first month alone. Nearly a fifth of the muscle gone within weeks. 1/6 gravity slows that collapse. It does not prevent it. The crew trains on resistance equipment daily, 2 to 2.5 hours at a stretch, more time than most people spend exercising in an entire week. On the space station, even that has never fully stopped the loss. Whether it works better here is untested. Nobody has run the experiment before this crew. The heart takes a third hit, and a quieter one. On Earth, it works constantly against gravity to push blood upward to the brain. Here, that resistance drops, fluid drifts toward the head and chest, and the heart, sensing what looks like too much blood already on hand, simply does less work. Total blood volume falls over the following weeks. The heart muscle loses mass from disuse, the same way an unused arm goes soft. Blood vessels lose their tone. The result is a heart less able to respond to sudden demand, a body more prone to dizziness and fainting, a system quietly deconditioned inside an uncontrolled physiological experiment that has never been run this long before. Whether that holds steady over years in 1/6 gravity, rather than the weeks measured on orbital stations, is completely unknown. Even the eyes may not be safe. Since around 2010, flight doctors have recognized a syndrome in long-duration crews: the eyeball flattening slightly, the optic nerve swelling, folds forming in the tissue behind the retina, all tied to the same fluid shift, pulling toward the head. Some affected astronauts never fully regain the vision they had before flight. Whether 1/6 gravity triggers the same slow reshaping is, like almost everything else about this body, not yet known. If it does, there is no way to grind new lenses on the moon. Spine, bone, muscle, heart, eyes, not one system spared. Not one fully understood. The crew did not come to the moon only to survive it. They came to find out, one slowly changing body at a time, what a human actually becomes after 1,000 days of carrying just 1/6 of its own weight. Whatever the answer turns out to be, there is no hospital here to catch what the body cannot hold onto on its own. No hospital catches the slow declines. But not everything on the moon happens slowly. A kidney stone does not care about a maintenance schedule, neither does a dental abscess, an inflamed appendix, or a heart that suddenly beats wrong. When one of those arrives, the crew discovers exactly what medical care on the moon actually means, and it is smaller than anyone wants to admit. One crew member carries advanced medical training, not a surgeon, not a radiologist, not a specialist of any kind. The kit at their disposal holds painkillers, antibiotics, anti-inflammatories, cardiac medication, wound care supplies, a portable ultrasound, a defibrillator, and a small tray of instruments for minor procedures. It has no MRI, no CT scanner, no blood for a transfusion, no anesthesia for anything beyond the smallest incision. Call it what it is: a well-equipped field clinic, dropped onto the most unforgiving terrain a field clinic has ever been asked to serve. Earth can still help, up to a point. A radio signal takes 1.3 seconds to cross the distance one way, roughly the lag of a slow video call, nothing like the 20-minute wait a Mars crew would face. Close enough that a flight surgeon on the ground can walk the medical officer through a diagnostic exam, study the ultrasound images, adjust a medication, talk through a set of symptoms in something close to real time. What that flight surgeon cannot do is perform the surgery, cannot deliver blood, cannot reach through the screen and take over. And if the problem is serious enough to need an actual hospital, the earliest a patient reaches one is 3 to 4 days away, a stretch longer than a holiday weekend spent getting steadily sicker, and only under ideal conditions, only if the return vehicle is fueled, checked, and sitting in the right position at the right moment. On some stretches of the mission, it may not be ready at all. Submarine crews live with something similar. So do the researchers who winter over in Antarctica, cut off from evacuation for months at a stretch. But here's what those comparisons miss. Those crews are not simultaneously losing bone density every month, absorbing radiation with no shield overhead, and breathing a fine glass dust with no known long-term ceiling. The moon does not just isolate the crew from a hospital, it actively manufactures the emergency that the isolation then makes fatal. While bodies wear down on their own private schedule, the walls around them are wearing down too, on a schedule of their own. Micrometeorites fall constantly and invisibly. No atmosphere out there to burn them up or slow them down, so every fragment arrives at its full travelling speed, somewhere between 10 and 70 kilometers a second, 30 to 200 times faster than a rifle bullet leaves the barrel. A 2025 study built on NASA's meteoroid engineering model estimated that a structure the size of the space station, sitting at the lunar South Pole, would take about 15,000 of these impacts every year, most weighing less than a millionth of a gram, a few as heavy as a small grape. Almost none of them get through. The habitat wall is built like a Whipple shield, a thin sacrificial layer standing apart from the main hull, built to catch an incoming particle and shatter it into a harmless spray before it ever reaches anything that holds pressure. Run the numbers, and a shielded habitat at the pole takes a real, wall-piercing hit only once every 42 years. That sounds like safety. It is not the whole story. Not a single dramatic breach. Thousands of small ones, every year, cratering the outer layer, clouding the camera lenses, dulling the windows, roughening the coatings that keep the habitat's temperature in balance. None of it punches through. All of it adds up. Over nearly 3 years, 15,000 impacts a year becomes a shell, quietly sandblasted from the outside, and the only way to repair any of it is to send a crew member back out into the same bombardment. Heat does its own separate damage. Every cycle still swings the exterior past that 300-degree line, and metal expands, contracts, expands again, joints flexing against joints built from materials that never move at quite the same rate. The space station cycles too, roughly every 90 minutes, but across a far narrower band, with some cushioning from a wisp of residual atmosphere. This cycle is slower and far more violent, and it never once eases up. No structure on Earth endures anything like it. This size, this amplitude, inside a vacuum. By the 20th or 25th cycle, inspection panels start showing what that means. A hairline crack along a weld seam, a fastener that has quietly lost its torque, a polymer gasket gone brittle years before its rated life. What all of that adds up to by cycle 34 is honestly an open question nobody can answer yet. And into that decaying shell, on legs that carry less bone than they did a year ago, the crew keeps stepping outside. Dozens of excursions by now, the same protocol each time. Suit check, depressurization, the work itself, return, repressurization, inspection. The tasks change. The risk underneath them does not. Unshielded radiation, a sharp edge of regolith that could catch a glove or a boot, a fall that low gravity turns awkward, and a stiff, pressurized suit turns slow to correct. In the first weeks, a stumble was nothing. A bruise, a laugh about it later. Months of quiet bone loss changed the arithmetic. The same stumble, the same patch of ground, and a hip or a wrist gives out instead of holding. The suit was never armor. It only ever bought time. Lose one crew member to a fracture like that, and the team does not lose one person's worth of trouble. It loses 1/4 of everything that person could still have done for however many hundreds of days remain, with no one else on the moon to take their place. The medical kit can splint the break. It cannot undo it. The body, the walls, the ground beneath every boot, all of it aging at once, all of it moving in one direction. What comes apart next is not the hardware at all. Bodies wear down on a schedule you can measure. The mind keeps a different clock. Decades of isolation research have mapped that clock with real consistency, and it runs in phases the crew cannot skip or shorten. The first 2 to 4 weeks bring something close to relief. Everything is still new. The habitat, the tasks, the black sky outside the viewport, all of it carries the charge of being among the first 4 people to try this. Motivation runs high. Alertness runs high. The hostility of the place has not yet had time to become boring. Boredom arrives around month 2, and it does not travel alone. Routines settle in. Novelty fades. The crew moves into patterns that function but no longer excite. And that is exactly when the small things start to matter. One crew member keeps leaving a tool in the wrong place. Another has a way of clearing their throat before speaking that starts to grate over weeks of constant proximity. None of this would register on Earth, where a person can walk into another room or outside or down the street. Here, personal space is measured in centimeters, and there is no door that closes off a person without also closing off a shared system everyone needs. The 4 were chosen for exactly this. Years of training selected for resilience, for flexibility, for the specific talent of staying productive inside a small sealed volume with the same 3 other people for a very long time. NASA's behavioral scientists have still catalogued what happens anyway. Pairs drift together and harden into an in-group and an out-group over disagreements that would be nothing anywhere else. Frustration with the unchangeable environment gets redirected at the nearest available target, a crewmate, and some withdraw, doing their duties competently while quietly opting out of anything social, leaving the others to carry the weight of holding the group together. There are countermeasures, shared meals on the schedule, a weekly private call with a psychologist on the ground, scripts for de-escalating an argument before it hardens. None of it is a cure, not close. It manages symptoms while the cause, 4 people, 1 volume, no exit, keeps generating more of them. A script that works well in month 3 can feel hollow by month 9, mostly because the specialist on the radio cannot sit in the room and cannot change the fact that tomorrow brings the same roster, the same numbers, and the same unresolved friction left over from yesterday. The clearest proof of how real this is did not happen on the moon at all. 6 volunteers spent 520 days sealed inside a mock spacecraft in Moscow, a stretch pushing a year and a half, fully aware of the schedule and fully volunteering for it. Sleep disruption showed up anyway. So did a steady drop in activity. One participant withdrew further and further as the second half wore on. None of it went away. That was Mars 500. And it ran on Earth, with an exit 1 door away the entire time. The friction of month 2 is not the hardest test. That test comes later, close to 3/4 of the way through any long confinement. A point mission psychologists call the 3rd quarter dip. The beginning carries the energy of arrival. The end carries the pull of going home. The 3/4 mark sits in between, past the point where novelty still helps, short of the point where the finish line starts to matter. On a 1,000-day mission, the dip centers near day 750, but its roots start earlier, somewhere around the close of year 1. What makes the moon uniquely hard on the mind is not distance. It is proximity without access. A station crew watches Earth fill half the sky, circling it every 90 minutes, with fresh faces rotating in roughly twice a year. This crew sees the same Earth, close enough to make out weather and coastline, close enough to reach by radio in under 2 seconds. Nobody's coming. Resupply lands on a schedule counted in months, not weeks. Rotation is not planned. The 4 who landed are the 4 who stay, for all 1,000 days, unless something breaks badly enough to force an early return. Antarctic winter-over crews live a milder version of the same trap, watch but unreachable, and the record on them is consistent. Irritability climbs, concentration frays, sleep frays with it. Something researchers call psychological narrowing sets in, a slow contraction of emotional range and initiative. On the moon, the landscape does nothing to interrupt it. No season changes, no weather rolls through. The same grey ground runs to the same sharp horizon, under the same black sky, and the only motion anywhere is the crawl of shadows across the regolith. A mind built to notice change finds none out there, and turns inward instead, toward whatever it finds waiting. Sleep pays for it too. A body raised on Earth runs on a roughly 24-hour rhythm. The moon's actual day, sunrise to sunrise, spans the same 29.5-day cycle, already stretching every other system in the habitat. And even with the lighting held on an artificial 24-hour schedule, the body seems to sense the mismatch. Sleep quality erodes through mechanisms nobody fully understands yet, and eroded sleep drags cognition down with it. Reaction time slows. Judgment tilts too cautious or too reckless by turns. Small procedural errors creep upward exactly where a small error costs the most. By the end of year 1, the accounting comes due. Roughly 365 days behind them. 12 full swings between 14 days of light and 14 days of dark. Bone density down, muscle mass down, a meaningful bite taken out of a career's worth of radiation allowance. Filters, sorbents, medical stock, food variety, all drawn down by a third or more. Nothing broke, nothing failed. That is the real accomplishment of year 1, and also the trap inside it because none of that decline flattens out. It keeps going, at the same rate, in the same direction. Ahead sits 635 more days. The mission is not yet 40% complete. Every filter already swapped will be swapped again. Every long night on stored power will return, a dozen more times. Every ache in the lower back will still be there tomorrow, and worse the week after. No single catastrophe waits out past day 365. Not a disaster. Not one failure anyone could point to. Something slower. Something the moon does better than any disaster ever could. And the long stretch ahead, the stretch where that slow repetition would be tested hardest, was only just beginning. Year 1 showed the crew the arithmetic. Day 700 is what that arithmetic looks like once it has kept running for another year on top of it. The date arrives without ceremony. No alarm sounds, no marker changes colour. The crew knows where they stand only because the calendar is one of the few things in the habitat still moving forward at a steady pace, while nearly everything else moves the other way. The consumable inventory is lighter, the equipment is older, the bodies are weaker. The gap between what the mission needs and what it still has narrowed since the first cycle, and it has not widened back once. By day 700, the crew has lived through roughly 24 complete lunar day-night cycles, 24 thermal swings past 300 degrees, 24 transitions from solar abundance into 2 weeks of darkness on stored power alone. The number sounds almost modest, the kind of count a person keeps on one hand and a thumb. Lived through is 24 layers of the same environmental weight, stacked one on the last, on every system the crew depends on. The dosimeter keeps a ledger the body cannot feel and the crew cannot ignore. Galactic cosmic rays deposit somewhere between 150 and 300 millisieverts a year, unshielded, and by now each crew member's cumulative dose likely sits above 300 millisieverts, closing in on 500. The career ceiling, roughly 600 millisieverts, is no longer distant. At the current rate, the final 300 days alone could press a crew member's total against it, or past it. And the trajectory does not level off. It cannot. No treatment undoes radiation already absorbed. No pill restores a strand of DNA broken 2 years ago, and repaired imperfectly. The cost? Elevated cancer risk, cardiovascular damage, cognitive effects still not fully mapped, will not come due until years or decades after the crew comes home, if they come home at all. Every entry on that ledger is permanent. The structure keeping them alive is aging on the same one-way schedule. More than 23 full thermal cycles in, Inspection logs show exactly what Year 1's fatigue warnings predicted. Fasteners on the exterior panels have measurably loosened, despite locking features built to resist that. Some sit unreachable without partial disassembly, hours of suited work for a single bolt. Polymer gaskets outside the pressurized volume are embrittling and cracking. Thermal coatings are microflaking, forcing the system to spend more power compensating for a coating not meant to still be doing this job. None of it alone is an emergency. Each is a point in a trend that, projected through the cycles still ahead, closes in on the design margins of hardware qualified for a fixed number of cycles. The habitat was built to survive this environment. Not for this long without the pressurized workshop back on Earth. Everything still runs back to one thin line stretching across roughly 384,000 kilometers of vacuum. A cargo vehicle reaches lunar orbit in about 3 days, the surface within a day after. Set beside Mars, months of transit, launch windows every 2 years. That proximity looks like an advantage, but it does not make the trip cheap. Every kilogram must be lifted clear of Earth's gravity, accelerated to translunar speed, and set down gently, and current estimates run from the tens of thousands of dollars per kilogram into 6 figures. A single flight carrying 1,000 kilograms represents tens to hundreds of millions of dollars, and over 1,000 days, several such flights are required. The chain runs through launch vehicles, landing systems, and an Earth-side manufacturing network, and a factory disruption or a launch failure could delay a flight the crew is counting on. Reserves are sized for ordinary delay, not a chain that breaks in 2 places at once. A 1,000-day mission built on resupply is, plainly, a remote outpost tethered to its home planet by a line that is long, thin, and replaceable by nothing found locally. The hoped-for alternative has a name: in situ resource utilization, using what the moon has instead of importing everything. And its distance from reality has to be stated plainly. Water ice mined from shadowed craters, purified into water, oxygen, fuel. Oxygen pulled from the metal oxides, making up close to 45% of lunar soil by mass. Metal recovered from regolith for repairs. None of it exists at operational scale on the surface. Ice extraction remains undemonstrated. No process has pulled oxygen from lunar soil fast enough to meet even one crew member's daily need. No mission has manufactured a spare part from lunar material in the field. Each capability sits between a lab bench and an early prototype, and that gap, measured against a process running continuously through vacuum, thermal extremes, and dust, with no repair infrastructure standing by, is measured in years. At day 700, the crew lives off what they brought, and what Earth keeps sending. Underground offers a different promise, one they cannot reach either. Lava tubes have been proposed as habitat sites since the 1980s, and in 2024, a study in Nature Astronomy produced the first direct radar evidence of an accessible one beneath a skylight in the Mare Tranquillitatis region, extending westward for a considerable distance, its full size and stability unconfirmed. Inside a stable tube under a modest thickness of basalt, radiation would fall by orders of magnitude, interior temperature would settle near a stable minus 20 degrees Celsius, and micrometeorite impacts would become irrelevant. But no robotic mission has entered a lunar lava tube. The European Space Agency's tethered micro-rover descent concepts remain design studies, nothing flown. Piling regolith over the habitat is a nearer alternative, and 2 to 3 meters of it would cut radiation exposure to something close to ISS levels. The raw material is unlimited. Moving it is not, requiring loaders that must themselves survive the same abrasive dust, wearing down every bearing they carry, and sintering regolith into solid blocks has only worked in laboratories on Earth. Neither is waiting for this crew. One promise remains standing, technically the whole time: the ability to leave. The return vehicle sits fueled and ready for the moment a failure outruns what the habitat can handle. Lunar escape velocity is only about 2.4 kilometers per second, a fifth of Earth's, so a crew that lifts off could be home within 3 to 4 days. That is the theory. The practice depends on that vehicle still working after sitting exposed to the same cycling and dust the habitat endures, without the daily attention the habitat gets. A pre-launch checkout would catch most problems. Not necessarily all of them. A frozen valve or a degraded battery could surface at the exact moment departure is most urgent. Earth is close, but not instantly reachable. A request for help travels there in under 2 seconds. A physical rescue still takes days. For nearly all of the 1,000 days, the 4 of them are functionally on their own. Day 700 was supposed to feel like a plateau, a long flat stretch before the final approach, not a plateau, a steady climb that never levels off. The radiation keeps accumulating. The fasteners keep loosening. Every proposed way off this tether, the ice, the oxygen in the soil, the lava tube, the shielded dome, is still sitting years away. And the return vehicle is a promise degrading in the open, the same as everything else. What the crew has, at day 700, is exactly what they arrived with. The habitat, the supply line, and each other. 300 days remained, to be crossed with nothing more than that. 300 more days passed the same way, the 700 before them passed. 1 gasket checked. 1 dosimeter read and logged. 1 increment added to a ledger that has never once gone down. Then day 1000 arrives, and it arrives the way almost every day on the moon arrives, without ceremony. The atmospheric readout shows nominal values. The power system reports adequate reserves. The water recycler runs its normal sequence. The dosimeters record another increment that will follow each of them for the rest of their biological lives. Outside, the regolith has not moved. The horizon has not changed. The silence beyond the hole is the same silence that met them on landing day, nearly 3 years earlier. Outside, nothing is different. Inside, everything is. The habitat is older now, carried through thousands of operating cycles by a crew that has learned its personality the way a sailor learns a ship. Which valve sticks when the temperature drops? Which sensor drifts when the dust loading climbs? Which breaker trips under a peak draw if nobody is watching the load? The crew's bodies are different too. Bone density down, muscle mass down, hearts and blood vessels deconditioned. A radiation total that will shape their medical charts for decades after they are home. Their minds are different as well, having lived the whole arc, the early relief, the friction, the long dip, and the quieter reconstruction of purpose that carried them through the stretch after it. So what does 1,000 days like this actually prove? Not colonization. A colony means growing your own food indefinitely, raising a next generation, building an economy, standing on its own once the ships stop coming. Nothing about 4 people living out of stored supplies in one sealed module resembles that. What it proves is narrower and more useful. That a human body can be kept alive for an extended stretch on a world that offers it no natural support at all. That every breath can be manufactured, every drop of water reclaimed, every watt generated or stored and spent. That a hazard, dust, radiation, cold, heat, low gravity, a slowly weakening skeleton does not have to be eliminated to be survived. It only has to be managed, continuously, cycle after cycle, for nearly 3 years without a single missed shift. There is no flag planting moment in that. The achievement is not a moment at all. It is an accumulation, close to 10,000 maintenance tasks completed correctly, roughly 10 a day, every day, for 1,000 days straight. 34 lunar nights survived on stored power alone. The last of them closed out weeks ago. Every filter changed before it failed. Every seal replaced before it leaked. Every radiation alarm answered inside the window the protocol demanded. Every disagreement between 4 people sealed in a metal container on a dead surface resolved before it could fracture the trust their lives depended on. 993 days ago, the readout said nominal, and that word meant almost nothing with 1,000 days still ahead of it. Now it is the only word that has held true, week after week, for 3 straight years. The moon sits 239,000 miles away. Its light and its radio delay only 1.3 seconds each way, close enough that a rescue vehicle feels like it should exist, but no such vehicle is standing by, and even if it were, it could not arrive in less than days. There is no hospital here, no fire department, no supply warehouse to walk to. The nearness that makes the moon feel almost within reach, the visible Earth overhead, the near-instant radio link, is exactly what disguises how alone the crew actually is. This is the closest world to Earth, and at the same time, the closest place where every one of Earth's protections stops working completely. No atmosphere, no magnetic field, no liquid water, no breathable gas, no thermal buffer, no living system of any kind. Nothing a human body needs exists here on its own. 1,000 days like this was never going to feel like founding a home under a new sky. It feels like keeping a submarine running that never gets to surface, every system demanding constant attention, every resource draining, every part of the machine aging, every body wearing down, while the world outside stays exactly as indifferent on day 1000 as it was on day 1. The moon does not storm, it does not hunt, it simply persists, unmoved, while everything the crew brought with them wears down against it like a blade, dulled slowly against stone. None of this makes the moon a second Earth. It cannot become one, not in 1,000 days and not in 10,000. It has never had the mass to hold a permanent atmosphere, the churning core to generate a magnetic shield, or the buried reserves of water and gas a real biosphere needs. It will never be terraformed. What 1,000 days proves instead is smaller and more honest, that human engineering, kept alive by human attention, can hold open one small pocket of livable air on a surface built to be hostile to every requirement of life. That the pocket holds, that the air stays breathable, the water stays clean, the power stays on through the dark, and the 4 people inside stay functional, cooperative, and alive. That pocket has a cost, and the cost is not measured only in money, though the money is enormous. It is measured in bone that will not fully return, in radiation that stays in the body permanently, in years spent inside a space smaller than most apartments, doing a repetitive maintenance on systems that kill in minutes if they fail, eating the same food, breathing the same recycled air, looking at the same unchanging grey horizon for nearly 3 years straight. Not explorers charging across a new frontier, not settlers building a life, technicians, caretakers of a machine they have slowly become part of, until the line between the crew and the habitat blurs into one human-rated life support loop. 4 people and a structure that would kill all of them within minutes if it stopped running. The moon may be the nearest place in the universe where nothing is free. Not air, not water, not warmth, not safety, not even time. Every second of this survival was purchased continuously by machinery built, launched, and kept running at extraordinary cost. 1,000 days proves that purchase can be sustained, that a crew can carry enough of Earth with them to endure almost 3 years on a world offering nothing back. It does not prove the moon is a home. It proves that people can survive somewhere that isn't one, and it leaves behind, in every dose reading, every worn-out seal, every quiet fatigue nobody has fully named yet, an honest record of what that survival cost. Not a triumph over the moon, not a defeat by it either, a transaction, 1,000 days of human life traded for the knowledge that people can endure where nothing invites them to stay, carried the entire way by the small, stubborn piece of earth they refuse to let fail. What that cost will still be asking of their bodies 20 years from now is a question none of them can answer yet, and will not be able to for a long time.